In this video, we're going to talk about the early models of the atom. The first thing we need to understand about the atom is that the arrangement of electrons resides outside of the nucleus and behaves in a wave-like manner. And if you want to think about waves, waves have wavelengths. So if you're at the ocean, it's basically the distance between the top of two waves or the bottom of two waves. And when we talk about waves as it applies to electrons, we always report the wavelength as lambda and how often the wave occurs as frequency, which is denoted as nu. And so we think about distance for wavelength, and when we talk about frequency, it's how many times that wave is being completed. And we typically use hertz, which is the same as 1/seconds. Now, waves can have many different speeds, but it turns out that electrons, and this applies only to electrons, move at the speed of light. They always have the same speed. And so all of these electrons moving at the same speed can be correlated to some wavelength of light. So we can get electrons excited. We can get them to emit light by moving an electron around the nucleus. So the first relationship we have to talk about is that the speed of light is equal to the frequency times the wavelength. So C equals lambda nu. And so anytime we're talking about an electron, we're talking about something that moves at the speed of light, which is 3 times 10 to the 8th meters per second. Although that does change slightly in our atmosphere, we consider it a constant, and that measurement is based off of the speed of light in a vacuum. Now, when we talk about moving electrons around the atom, we need to apply some energy in order for the electron to move from a state that it currently is in. So think about a game of pool. You've got the cue ball, and it's just going to sit there unless you apply some energy to it. Well, electrons don't sit there, but they also don't move away or closer to the atom's nucleus unless it gets some energy applied or taken out. And Einstein ended up winning the Nobel Prize for what's known as the photoelectric effect, which basically he was able to take and find a way of determining the amount of energy required to move an electron from one location to another one. And so the energy is equal to something known as Planck's constant times the frequency of the electron. So again, we have to think about frequency in hertz. Hertz is the same as 1/seconds. So when we're calculating or we're trying to determine how much energy we need, we have Planck's constant, which is always the same value, and we need to make sure our frequency is in terms of seconds. So what do we know about the energy of electrons and electromagnetic radiation? Well, there's a whole spectrum available to us, ranging from very large wavelengths, meters, kilometers, all the way down to wavelengths smaller than the size of a proton or neutron. These are some incredibly small distances that waves can complete. Now, when we talk about electromagnetic radiation, you may be familiar with the term photon. If you're not, that's okay. A photon is a massless particle that only has energy, and it follows the rules that we've described for describing light. Now, regardless of the wavelength of the photon, we can always classify wavelengths based on where they fall in some spectrum. And don't worry about knowing the exact cutoffs for an exam, but we do have certain regions or certain distances which we classify wavelengths in. So anything that's the size of 1/10 of a meter or larger, we call radio waves. Radio waves have relatively low frequencies, so things occurring 10,000, 100,000, a million, 10 million times per second. Those are what we consider low frequencies. And they're low energy waves. Remember, wavelength is tied to energy, so relatively low wavelength means relatively low energy waves. Microwaves go from about 1/10 of a millimeter all the way up to 100 centimeters. So, still something we can kind of fathom, something we could measure, maybe if we had a really sensitive a ruler and we could visualize these things. But the wavelengths, they're starting to get small. Infrared, which we typically use in heat lamps, constitute even smaller wavelengths, and then we get to this very narrow region of 400 to 750 nanometers, which is known as the visible region. That's what our rods and cones are accustomed to, and that's basically our world. We see from 400 nanometers all the way up to 750, and every color of the rainbow that we know of is somewhere in this region. Below that, we have ultraviolet light, and now we're starting to talk about photons that occur often enough in short enough distances that they can actually start doing some biological harm. Anything visible and above we don't worry about for the most part. Microwaves, there's one or two we worry about. But ultraviolet waves are wavelengths that can actually break chemical bonds. Nothing above the visible spectrum can break a chemical bond. Although it can get molecules to get excited, you can't actually break a bond until you hit the ultraviolet region. X-rays are even smaller than that, followed by gamma rays. Gamma rays are the smallest and most energetic waves out there. They are the most dangerous, and the best way to protect yourself from gamma rays is putting as many atoms between you and the gamma ray source as possible. So why do we talk about these different regions of the electromagnetic spectrum? And that is because when we started looking at elements and applying energy to them, we wanted to understand why they gave off the different colors they do. So this is a lamp full of hydrogen gas. And what happened was we were able to take a hydrogen lamp, put it through a lens to get a very narrow beam, and then run that beam of light through a prism. And what we found was that the light separated into 4 distinct wavelengths. So we had a very discrete spectrum. Well, each one of these lines that makes up the purplish glow or neon glow to the hydrogen lamp is a component of the overall light that you see. So hydrogen has 4 distinct wavelengths, which means there are 4 distinct energies involved in producing that light. So there's an energy associated with 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. Well, this translates into 4 unique quanta of energy. So each line represents a very specific amount of energy. And so when we talk about quanta of energy, we're talking about a specific amount of energy. Hydrogen, we see 4 quanta, or we have 4 lines, because there are 4 transitions that an electron in a hydrogen atom can go. Now, we see 4, but in reality, there's many more lines than that. And the reason we only see 4 is that the 4 we see fall in the visible spectrum. There are other transitions we know about. We've detected them. But what we know is that each transition involves an electron moving from one location to another. It's either moving closer to the atom or it's moving farther away from the atom. So these electrons are getting bounced around, but they're arriving at very specific spots. And what it turns out is that these spots can actually be correlated in terms of integer numbers. So if we start thinking about the area around the nucleus of an atom as an apartment building, electrons occupy the first floor, the second floor, the third floor, etc., but they don't occupy any distance in between. So there's no 1.5 floor or 13 3/4 floor. You're either on the first floor or the second. You can't be anywhere in between. So this means that there are very specific regions around the nucleus of the atom that an electron is allowed to be at, and it can't be anywhere else. So modeling the electron, we first got what's known as the Rydberg equation. The Rydberg equation says that the energy involving an electron moving between two levels can be calculated in terms of whole numbers. And so NF represents the floor you end up on, N sub I represents the floor you started on, H is Planck's constant, C is the speed of light, R sub H is the Rydberg constant. So we can calculate the energy to get an electron to jump from one spot to another. And that was a tremendous leap forward in our understanding of the atom. So electrons have discrete levels which they occupy, and we call these certain levels quanta. So does this work with other elements was the next question that was posed. And so looking at other elements and their fingerprint line spectrum, we see that helium, sodium, neon all have very specific jumps. They have regions where they're allowed to be and regions where they're not allowed to be. And so we start gathering these fingerprints of the elements. And we actually still use these fingerprints today when we look at stars so we can determine what the composition of the star is. So our sun, we know what the atomic composition is. It's not that we went up to the sun and took a scoop and took it back to the lab. We actually profiled all the elements of the periodic table. We looked at what wavelengths that they have, and we could tease together this fingerprints, these series of fingerprints, to arrive at a combination that represents the wavelengths that are produced by the sun. So, does this work for all elements? Well, the Bohr model, which is essentially what Rydberg was basing his equation on, found that there were only certain radii that were allowed to be permitted. So an electron is allowed to be in a permitted state. It has a very specific energy associated with that, and you can't put in extra energy to get the electron to move halfway between two allowed states. It's either in one spot or the other. It either takes all the energy it's given or it doesn't take it at all. So energy is required to move an electron further away. And that kind of makes sense. You got to climb stairs, you got to put some energy into it. But if energy, or if an electron moves closer to the nucleus, then energy is released. And so what we see when we turn on a lamp or we look at the sun is the energy that's being released from electrons falling back to the nucleus, and they're trying to get as close as possible. But they can take a series of steps to get there. Now, can we use Rydberg's equation with other elements? And the answer is no, we can't. Rydberg's equation only worked for hydrogen because it was modeled after a single positive charge interacting with a single negative charge. That is, there's only one proton interacting with one electron. All other elements have more than one interaction. They have protons interacting with neutrons, protons interacting with multiple electrons, electrons interacting with each other. So it becomes quite complicated very quickly. So the one thing they all have in common is that there is specific amounts of energy which are unique to each electron, or each atom. So every atom has a very specific spot where it allows its electrons to go.